What's beneath your feet right now? There's the floor of the house you're sitting in, or perhaps you're in your bed. And on the other side of the earth, someone else is standing or lying in a place just like yours, asking the same question. Now look up. What's above you? There's a ceiling, maybe the sky, maybe clouds, maybe stars. And then, the atmosphere ends. Space begins. And inside that space, there's the solar system, planets, comets, asteroids. And all of that ends. But what comes after? What exists above the solar system? This question might seem simple to you. Maybe you're thinking space is empty. Maybe you're saying there's nothing, just darkness. But the answer is far bigger and more complex than you think. Because above the solar system, where the sun's gravity ends, there exists some of the most mysterious, unknown, most extreme structures ever observed in the universe. And most of them, even the most advanced telescopes in human history, have not yet been able to fully see. Tonight, I'm going to tell you what lies beyond the boundaries of the solar system. We'll start from the very first region just above that boundary and embark on a journey that grows ever deeper, ever more mysterious. And by the end of this journey, everything you thought you knew about the universe will look a little different. If you enjoy these kinds of journeys that make you see the universe through a different lens, don't forget to click the like button and subscribe. It truly makes a difference in keeping these videos going. Let's set out together. Let's begin. First, let's clarify something. Where is the boundary of the solar system? This question is very complex, because the solar system has more than one boundary, and each of these boundaries defines a different physical reality. First boundary, Neptune's orbit. When most people think of the solar system, they see Neptune as the last planet. This is correct information, but incomplete. Neptune is approximately 30 astronomical units from the Sun. What is an astronomical unit? The distance between Earth and the Sun. So Neptune is about 30 times farther from the Sun than Earth. This seems like an unbelievably large distance. But compared to the real boundary of the solar system, Neptune is almost right next to the Sun. Second boundary, the heliosphere. This is the region where the particles emitted by the Sun, the solar wind, are balanced by the pressure of the interstellar medium. Here, the solar wind stops, and this boundary is much farther out than Neptune, approximately 100 astronomical units away, more than 3 times the distance to Neptune. And we directly observed this boundary. How? Voyager 1, the farthest human-made object ever sent, launched in 1977, and in 2012, for the first time in history, a human-made object crossed the boundary of the heliosphere. It exited the heliosphere and entered interstellar space. That moment was an incredible moment in human history, but at the same time an incredibly humble one. Because when Voyager 1 crossed this boundary, it was still far from the real boundary of the solar system. It was still inside the solar system. Were you surprised? Because the third and true boundary of the solar system is much farther away. And this boundary is known as the Oort cloud. The Oort cloud. You may have heard this name, or perhaps not. But this structure is the outermost layer of the solar system and at the same time its most mysterious region. And truly understanding it is the first and most important step of this journey. A Dutch astronomer named Jan Oort noticed something very interesting in 1950. When he examined long-period comets coming from very distant places, the directions from which these comets came were completely randomly distributed. They came from the north, from the south, from the east, from the west, from every direction. They had no relationship to the ecliptic plane. In other words, they were not synchronized with the movements of the planets orbiting the Sun. This was a very important clue. If these comets were coming from the inner regions of the solar system, they would be moving in a specific plane. But they were coming from every direction. This meant These comets were coming from a vast spherical cloud that completely surrounded and enveloped the sun. From every direction, from every angle, as if the sun had been enclosed inside a giant sphere. And this cloud, theoretically, would have to be enormously large. How large? It extends from approximately 2,000 to 100,000 astronomical units from the sun. Its outermost point extends halfway to Proxima Centauri, the nearest star to the sun. So the solar system, including the Oort cloud, occupies nearly half the distance between two stars. This number is extremely difficult to grasp, but let me explain with a simple example. Voyager 1 was launched in 1977, and since that day, without stopping, it has been traveling at approximately 17 kilometers per second. That's more than 50 times the speed of sound. And at this tremendous speed, it would take Voyager 1 approximately 300 years to reach the inner boundary of the Oort cloud, and approximately 30,000 years to exit the outer boundary of the Oort cloud. 30,000 years, without stopping, 17 kilometers per second. And even then it will have only left the solar system. Now let's look at what's inside the Oort cloud, because this region is not just empty. There's a lot inside it. According to estimates, the Oort cloud contains trillions of objects, masses of ice, pieces of rock, organic compounds, most likely water ice, methane ice, ammonia ice. The vast majority of these are remnants left over from the formation of the solar system. 4.6 billion years ago, matter that was flung outward when the sun and planets formed. And since that day, under the very weak gravity of the sun, at these tremendous distances, they have been slowly orbiting. For billions of years, silently, and occasionally, due to the close passage of a star or galactic tides, one of these objects changes its orbit and begins a long, slow journey lasting millions of years toward the sun. When it reaches the inner solar system, it warms from the sun's heat. The ice evaporates, and that magical tail forms. We call it a comet. So every long-period comet you see in the sky comes from the Oort cloud, one of trillions of objects. Having waited silently for billions of years, it has finally begun that long journey toward the sun. This thought alone is fascinating. But now let's come to a much more interesting truth. The existence of the Oort cloud is theoretically very strongly supported, but we have never directly observed it. No telescope has ever seen an object of the Oort cloud in place, that is, there at that tremendous distance, because they are so far away and such small objects that direct detection with today's technology is impossible. We only see the evidence, the incoming comets, and by calculating the orbits of these comets, we look at where they came from. The Oort cloud is a structure we know exists through indirect evidence, but have never seen, and this makes it both fascinating and unsettling. Now, before we move beyond the Oort cloud, let's pause for a moment to grasp the reality of where we are. Our solar system is located in one of the arms of the Milky Way galaxy, approximately 26,000 light-years from the center of the galaxy, in a spiral arm known as the Orion Arm. And this position is extremely important, because regions close to the center of the galaxy are extremely dangerous. There is high radiation. There are far too many stars. Gravitational interactions are very intense. But in this relatively calm region where we are located, our solar system can be protected and complex life can be made possible. But even in this calm region, there are fascinating things around our solar system, and the first of them begins right after the Oort cloud: interstellar space. This region is the in-between zone where one star system ends and another has not yet begun. And this region is not empty at all. There is interstellar matter. There is interstellar gas. There is interstellar dust. There are cosmic rays. There are magnetic fields. And all of these form an environment that is constantly moving, constantly interacting. But the most interesting of all is this. In this interstellar space around our solar system, there is an extremely special structure. This structure is called the local bubble. And understanding the structure means understanding why our solar system is in such a special position. The local bubble is a region approximately 300 light-years wide, made of extremely sparse gas and dust, inside which our solar system resides. This region is much less dense than the surrounding interstellar medium. And this sparseness is not coincidence. Millions of years ago, a series of supernova explosions occurred in this region. These explosions blasted the surrounding gas and dust outward and left behind this bubble. We are currently inside this bubble, and this position gives us important advantages. Lower density interstellar matter means our solar system is under less pressure. The heliosphere in this sparse environment can form a much larger and more protective shield. And this shield largely prevents harmful cosmic rays and interstellar winds from entering the solar system. So our existence may partly owe itself to being inside this bubble. This thought is both fascinating and humbling. Now let's step back one more time and look at the big picture. We asked what exists above the solar system. And so far we have arrived at these answers. There is the heliosphere boundary. There is the Oort cloud. There is interstellar space. There is the local bubble. But these are only the beginning. In this journey we will go much deeper. We will look at much larger structures. And at every step we will once again feel how vast and how complex the universe is. In the next section, we will look at what really exists in the interstellar space beyond the Oort cloud, how our sun travels through this environment, and how this journey may have had effects on life on Earth over millions of years. Because the solar system is not stationary. It moves, and this movement is far more dramatic than you think. Now close your eyes for a moment, and think about this. Right now, at this very moment, the solar system is orbiting the center of the galaxy at approximately 220 kilometers per second. Since the beginning of this video, you have traveled thousands of kilometers together with the solar system, making a journey through the Milky Way. And in that vast space through which this journey passes, above, below, on every side, all the structures we spoke of in this section surround you. They're real and still waiting to be explored. The sun is moving. This sentence looks simple. Maybe you already knew. You'll say, yes, the sun also orbits the center of the galaxy. But now I'm going to tell you something different. The sun doesn't just orbit the center of the galaxy. It also oscillates up and down relative to the galactic plane, like a horse on a carousel. It moves in a circular path and also rises up and comes back down. And this oscillation may have affected life on Earth. In this section, I'm going to tell you the following. How living, how dynamic, and how dangerous a place the interstellar environment above the solar system is. How our sun travels through this environment. And how this journey may have shaped life on Earth over millions of years. Because the space above the solar system is not just empty space. Things happen there. Very big things. And these things directly affect the conditions that determine whether you exist or not. First, let's grasp the true speed of the sun. The sun orbits the center of the galaxy at approximately 220 kilometers per second. That's more than 640 times the speed of sound. A full orbit at this speed takes approximately 225 to 250 million years. This is called a galactic year, also called a cosmic year. And since the formation of Earth, the solar system has completed approximately 18 to 20 full orbits around the center of the galaxy. But here is the truly interesting point. During this orbital motion, the sun doesn't remain stable relative to the galactic plane. Approximately every 60 to 70 million years, it rises above the galactic plane, then returns to the plane, descends below the plane, then rises again. This oscillating movement continues up and down with a period of approximately 30 to 35 million years. And why does this oscillation matter? Because when passing through the galactic plane, the solar system encounters a much denser medium of matter. The density of stars increases. Gravitational interactions intensify, and these intensified interactions disturb objects in the Oort cloud, disrupting their orbits and sending showers of comets inward into the inner regions of the solar system. Some paleontologists and astrophysicists have tried to link these cyclical comet showers to mass extinction events on Earth. So does that 30 to 35 million year period overlap with the major mass extinctions in Earth's history? This hypothesis is still debated, not definitively proven, but the thought itself is extraordinarily striking. The sun's journey through the galaxy may be determining the cycles of life on Earth. Now let's look more closely at the environment through which this journey passes: interstellar space. Interstellar space is the area between two star systems, but this space is not empty at all. It contains various components called interstellar matter, and each of these components is individually fascinating. First, interstellar gas. The majority of this gas is hydrogen. Compared to its density inside the solar system, it is extremely sparse. While inside the solar system there are billions of atoms per cubic centimeter, in interstellar space this number on average is only a few atoms per cubic centimeter. But despite this incredible sparseness, the total mass of this gas is extremely large, because interstellar space is unimaginably large. Second, interstellar dust. This dust is the remnant of stellar deaths. It forms in supernova explosions and when old stars shed their outer layers. It contains elements like silicon, carbon, iron, and magnesium, and this dust is the raw material for future stars and planets. A significant portion of the matter that today makes up the Sun and our planets came from dust particles produced inside other stars billions of years ago and scattered into space by supernova explosions. The story of the iron atom in your body may trace back to the core of another star billions of years ago. Third, cosmic rays. This is one of the most striking components in interstellar space. Cosmic rays are high-energy particles moving at close to the speed of light. Protons, helium nuclei, nuclei of heavier elements. Their sources are various. Supernova remnants, active galactic nuclei, neutron stars. These particles are constantly trying to enter our solar system. But the heliosphere, the magnetic bubble created by the Sun, blocks the vast majority of these particles. If the heliosphere didn't exist, Earth's surface would be exposed to far more cosmic ray bombardment. And this bombardment damages DNA, increases cancer risk, threatens complex life. So the heliosphere is an invisible shield protecting life on Earth. And the strength of this shield changes according to the conditions the Sun encounters as it passes through the interstellar environment. Now let's come to a much more concrete example. Approximately 2 to 3 million years ago, the solar system passed through a region of the interstellar environment that was much denser than normal. This region is called the local fluff. And during that period, the strength of the heliosphere decreased. More cosmic rays entered the solar system. Some researchers suggest that this period may overlap with climate changes. Some even discuss whether the period when the first ancestors of humans appeared may be related to this process. More cosmic rays could mean more cloud formation. More clouds could mean a cooler climate, and these climatic changes could mean the drying of Africa and the reduction of forests. This may have forced our ancestors to descend from the trees and walk upright. So the solar system's journey through the interstellar environment may have played a role in the existence of humanity. You realize that this thought is both fascinating and mind-bending. Now let's look at the Sun's neighbors in this journey, the nearby star systems. Our nearest neighbor is Proxima Centauri, approximately 4.24 light-years away, a red dwarf star, and there are planets around it. The planet called Proxima b is in the habitable zone of the star. Can water exist in liquid form? We don't yet know this for certain, but there is a possibility. Proxima Centauri is a very active star, produces powerful stellar flares. These flares send large amounts of radiation to the planets around it. This radiation may make the surface of Proxima be difficult for life, but perhaps there are geological or atmospheric protection mechanisms. Perhaps there is life underground or in the depths of oceans. We don't know yet. Our second nearest neighbor is the Alpha Centauri system. This triple star system, of which Proxima Centauri is also a part, is approximately 4.37 light-years away. Alpha Centauri A and Alpha Centauri B are stars very similar to the Sun, and recent research suggests that planets may also exist in this system. The third nearby neighbor is Barnard's star, 5.96 light-years away, one of the fastest-moving stars. It moves across the sky at approximately 140 kilometers per second, and it is getting closer. In approximately 10,000 years, it will reach its closest point to our solar system. But even this closest approach, by astronomical standards, will be approximately 3.75 light-years. So not even our Oort clouds will touch. Now let's come to a very interesting reality. The solar system is not stationary. The neighboring stars are not stationary either. Everything is moving, and these movements change the solar system's neighbors over time. Approximately 1.35 million years ago, a star called HIP 85605 passed quite close to our solar system. According to estimates, this star may have even entered the Oort cloud. Such a passage could seriously disturb the orbits of objects in the Oort cloud, and could send many comets into the inner solar system. In the future, such close passes will occur again. Approximately 1.3 million years from now, a star called Gliese 710 will pass extremely close to our solar system. According to current calculations, this star will come close enough to enter the Oort cloud, and this passage could cause the Oort cloud to be seriously disturbed. But even these close passes are meaningless on a human scale. The closest point of Gliese 710 will be approximately 13,000 astronomical units from our Sun, still in the outermost regions of the Oort cloud. Interstellar neighborliness is far too vast to be imagined on a human scale. Now let's come to the most dramatic part of this journey. Our solar system is currently in a very special region. We said inside the local bubble. But have you really thought about where this bubble came from? This bubble is the trace left by a series of supernovae that exploded in this region millions of years ago. At least 10, perhaps 20 supernova explosions. Each one blasted the surrounding gas and dust outward. Each one sent out enormous energy waves. And these explosions followed one after another. One exploded, its wave spread. Then another. And these chain explosions formed a vast and sparse bubble approximately 300 light-years in diameter. We are currently inside that bubble, and this bubble is still expanding. Its edges are colliding with the denser interstellar matter around it. And in these collision zones, new stars are being born. So the series of supernovae that created us is, after its destruction, raising new stars. This cycle is one of the most fascinating features of the interstellar environment. Stars are born, live, die. Their deaths scatter new matter into space. This matter forms new stars, and each generation contains heavier elements than the previous one. Each generation enables a richer chemistry than the previous one. Our Sun is a third-generation star. That means the matter that formed the Sun has passed through at least 2 previous generations of stars. Each generation produced heavy elements through thermonuclear processes. And these elements today make up Earth, the oceans, the atmosphere, and you. You are the product of billions of years of stellar evolution. Now let's come to the deepest point of this section. The interstellar space above the solar system is not just a passive environment affecting our solar system. It is an active environment, constantly changing, constantly moving, constantly interacting with our solar system. And these interactions contain both threat and opportunity. Threat. When passing through denser regions of the interstellar environment, the heliosphere may weaken. Cosmic ray bombardment may increase. The Oort cloud may be disturbed. More comets may come to the inner solar system. Opportunity. Organic molecules and dust particles in the interstellar environment, when entering the solar system, may be carrying the materials needed for life. The panspermia hypothesis says exactly this. Life can spread through the galaxy. Life from one planet can be seeded on another. This hypothesis is still debated, but organic molecules detected in the interstellar environment give serious support to this hypothesis. Glycolaldehyde has been detected in interstellar space. Precursor molecules to amino acids have been detected. Water ice has been detected. All of these are the raw materials of life, and they are everywhere, in that vast space above our solar system, in particles floating between star systems, perhaps entering and leaving our solar system once every billions of years. Life may be seeded throughout the galaxy, and we may be a product of that seeding. Now let's look at a much more interesting feature of interstellar space. This space is not just a homogeneous environment. Inside it, there are regions of different densities, different temperatures, different properties. And these regions are constantly interacting with one another. For example, there are cold molecular clouds. These clouds are the densest regions of the interstellar environment. Their temperatures are close to absolute zero, close to minus 270 degrees. But they contain extremely complex organic molecules inside them. And these clouds are the birthplace of new stars. Through gravitational collapse, these clouds densify, heat up, and finally a new star ignites. In the Milky Way, there are regions actively experiencing star birth right now. The Orion Nebula is the most famous of these, approximately 1,300 light-years from Earth. And inside it, hundreds of new stars are being born right now. Some of them have protoplanetary disks around them, meaning planets are beginning to form. Think about this. Right now, in real time, new solar systems are forming in our galaxy. And perhaps in some of these systems, billions of years from now, someone will look up at the sky and wonder about the silence of the universe. Now put together what we talked about in this section. We asked what exists above the solar system. And in this section, we arrived at these answers. The solar system is moving. It orbits the center of the galaxy and oscillates relative to the galactic plane. This movement leads to the disturbance of the Oort cloud, comet showers, and perhaps cycles of mass extinction on Earth. Around the solar system, there is the interstellar environment. This environment is active and dynamic. It contains cosmic rays, interstellar gas, dust, and organic molecules. The heliosphere manages this environment like a shield, and the strength of this shield changes according to the environment the solar system passes through. In the close vicinity of the solar system, there are other star systems. These stars are moving, occasionally making close passes. These passes can disturb the Oort cloud, and the solar system is located inside the local bubble. This bubble is the trace left by a series of supernovae that exploded millions of years ago. And this position plays a critical role in protecting our solar system. In the middle of all of this, you are here, on a small planet, orbiting the sun, accompanying the sun on its journey through the galaxy, and aware of the vast, complex, living environment through which this journey passes. This awareness is not trivial, because the space above the solar system is not a reality completely disconnected from you. That space is in constant interaction with you, every day, every second, Right now, as you watch this video, thousands of cosmic ray particles are passing through your body. The heliosphere blocks most of them, but not all. Some pass through the atmosphere, some pass through you. They come from interstellar space, perhaps from supernova remnants. You are a being in constant contact with the interstellar environment. This thought is both unsettling and fascinating. It makes you feel both small and large, both alone and connected. In the next section, we will take this journey to a much deeper point. We'll look at the structure of the Milky Way galaxy in which our solar system resides. We'll see how dramatic and how dangerous the galactic center is. And we'll understand why our solar system's position within the galaxy is so critical for life. Because we are not just on a lucky planet. We are in a lucky galactic position. And every detail of that position seems perfectly calibrated for you to be able to exist. Now close your eyes, rest, and think about this. Right now, the solar system is traveling at 220 kilometers per second. You are traveling with it. Around you, on all sides, all the structures we spoke of in this section are there. Cosmic rays, interstellar gas, organic molecules, moving star systems, all real, all there, and all very close to you right now. There is a monster at the center of the galaxy. This sentence is not a metaphor. It is real. At the very center of the Milky Way galaxy, there is a supermassive black hole called Sagittarius A star. Its mass is equivalent to approximately 4 million solar masses. And this black hole sits silently at the heart of our galaxy, pulling everything, shaping everything, and around it, creating one of the densest, most chaotic, most dangerous environments observed in the universe. We are 26,000 light-years away from this monster, and this distance may be one of the most fundamental reasons we exist. I end this section, I'm going to tell you the following. The structure of the Milky Way galaxy. How dramatic and how dangerous the galactic center is. Why the position of our solar system within the galaxy is so critical. And why, to understand what lies above our solar system, we need to use the entire galaxy as a frame. Because the question of what's above the solar system actually turns into this question. Where are we in the galaxy? And the answer to this question is both surprising and profound. First, let's grasp the true size of the Milky Way. The Milky Way is a spiral-armed galaxy. Its diameter is approximately 100,000 to 120,000 light-years. Its thickness near the center is approximately 10,000 to 15,000 light-years, and it contains 200 to 400 billion stars. Think about this number. 400 billion, each one a sun. Each one might have planets around it. Each one might have Oort clouds around it. Now imagine this galaxy as a city. At the central square, that enormous black hole is there. The regions close to the center are the city's most crowded, loudest, most dangerous neighborhoods. Stars are very close to one another. Supernova explosions are frequent. Radiation is intense. Gravitational interactions are violent. We are in this city's suburbs, in a quiet, relatively isolated corner, far from the central square, far from the noise. And this distance is saving our lives. But being in the suburbs doesn't mean being completely safe. The suburbs have their own dynamics. And these dynamics make the space above the solar system extremely interesting. Let's look more closely at the structure of the Milky Way. Our galaxy consists of several main components. First, the galactic center region. This is the densest part of the galaxy. Around the central supermassive black hole, billions of old stars have formed a spherical structure. This is called the galactic bulge or protrusion. In this region, stars are so dense that the night sky would seem constantly bright. Stars close in every direction, powerful light in every direction, but also danger in every direction. planets near the galactic center are subjected to intense radiation bombardment. Closed stellar passages can disrupt planetary orbits. And periodically, when the black hole at the galactic center becomes active, it releases enormous energy bursts. Sagittarius A** is currently relatively quiet, but it has had active periods in history, and the energy it released during these active periods was felt throughout the galaxy. Even traces of Sagittarius A**'s active period from approximately 2 million years ago have been detected. These enormous structures, known as the Fermi bubbles, extend thousands of light-years north and south from the galaxy, away from the galactic plane. 2 million years ago, the trace of an erupting black hole is still there, still visible. Second, the spiral arms. The most distinctive feature of the Milky Way is its spiral arms. These arms extend from the galactic center and curl across the galactic plane. Each arm contains dense star-forming regions, bright young stars, and large molecular clouds. There are 4 main spiral arms: the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm. Our solar system is located in a region between these main arms. This region, called the Orion arm or local arm, is a smaller structure extending between the Sagittarius and Perseus arms. And this in-between region is much calmer compared to the main arms. Is this calm a coincidence? Most likely not. In the main spiral arms, star formation is much more intense. This means far more supernova explosions, far more radiation, far more violent gravitational interactions. In this environment, planetary orbits can be disrupted much more easily, and maintaining the long-term stability needed for complex life is much harder. But we are in the calm region between these arms, and this calm region allowed our solar system and Earth to remain relatively stable for billions of years. Third, the galactic halo. This is a large, spherical region extending far beyond the galaxy's visible disk. There are very few stars in the galactic halo, but there is a great deal of dark matter. The globular star clusters found in the halo contain our galaxy's oldest stars, stars 12 to 13 billion years old, structures formed in the early periods of the universe. And these globular star clusters open the door to a very interesting thought. If life began in these star clusters formed in the early periods of the universe, that life could be billions of years more advanced than us. In the early period of the universe, heavy elements were scarcer. This means more difficult conditions for life. But a civilization that could overcome those conditions may have advanced beyond what we can even imagine today. This thought adds a new dimension to the Fermi paradox, and it once again shows why the space above the solar system is so fascinating. Now let's look more closely at the dangers of the galactic center. The region around Sagittarius A** is truly an incredible environment. Just around the black hole, there is an accretion disk made of gases reaching temperatures of millions of degrees. This disk emits X-rays and gamma rays. Around it, stars are orbiting the black hole at incredible speeds, some approaching close to 2% of the speed of light. The orbits of these stars provided one of the strongest confirmation evidences of Einstein's general theory of relativity. The precession effect resulting from the curvature of spacetime can be clearly observed in the orbits of these stars. And in 2019, when a cloud near the galactic center called G2 approached Sagittarius A**, scientists observed how the black hole interacted with this cloud. The cloud elongated and changed shape under tidal forces. But the expected dramatic flare did not occur. Sagittarius A** remained relatively calm at that moment. This also shows us the behavior of the black hole at the galactic center is not entirely predictable, and what could happen during an active period remains largely uncertain. Now let's address our solar system's position within the galaxy in a much more concrete way. there is a concept called the galactic habitable zone. This concept is the galactic scale equivalent of the biological habitable zone. Just as there is a zone around a star where water can remain liquid, the galaxy also has a region where complex life is possible. This region is far enough from the galactic center to not be too close, but close enough to the galactic edge to not be too far. Why is it necessary not to be too close to the galactic center? Because the dangers there are too great. Radiation is too dense. Stellar passes are too frequent. Energy bursts from black holes are too violent. For the long-term stability of complex life to be maintained, it needs to be sufficiently far from these dangers. Why is it necessary not to be too close to the galactic edge? Because their heavy elements are not sufficiently abundant. In the outer regions of the galaxy, star formation history is much shorter. That means fewer supernova explosions, less production of heavy elements. Elements like carbon, oxygen, iron, and silicon are necessary for the formation of planets and life. And these elements are insufficient in the outer regions. Our solar system, however, is in a perfect position between these two extremes, sufficiently far from the galactic center, protected from dangers, sufficiently inside from the galactic edge, rich in heavy elements. Is this position random or chosen? Of course it wasn't chosen, but it may not be random either. There is a concept called the anthropic principle. This principle says, because we are here, we observe here. That is, we observe the conditions that make our existence possible. Because we cannot exist under other conditions, we cannot observe those conditions. This is a philosophical approach, but it carries extremely strong meaning in the context of the galactic habitable zone. Now let's look at our movement through the galaxy once more, but this time from a much larger perspective. The Sun orbits the center of the galaxy. During this orbit, it sometimes enters spiral arms, sometimes exits them, and when inside the arms, it encounters a much denser environment. Some researchers suggest that during the periods when the solar system passes through spiral arms, the density of interstellar dust increases, and this increase in dust may reduce the solar radiation reaching the Sun. Reduced solar radiation may lead to cooling of Earth, and this may trigger ice ages. So ice ages on Earth may be influenced not only by our planet's internal dynamics, but also by our position in the galaxy. This hypothesis is still debated, but the thought itself is enormously fascinating, because it tells us this: life on Earth is not independent of galactic scale processes. Everything is connected. Everything affects everything else. Now let's look at some much lesser known but extremely interesting features of the Milky Way. At the center of our galaxy, around the supermassive black hole, there is a special cluster of young stars moving at extremely high speeds. How can these stars exist so close to the black hole? The molecular clouds needed for star formation should be torn apart by the black hole's tidal forces. But the stars are there. This is called the young stars paradox, and it has no complete solution yet. Perhaps these stars formed much farther from the black hole and later migrated inward. Perhaps another mechanism was at work. We don't know, and not knowing makes this area even more interesting. Our galaxy has other interesting features too. It was discovered that the Milky Way's disk is not flat. It is actually slightly curved and warped, like the edges of a vinyl record curling slightly. And this warping most likely stems from galactic interactions in the near past. The Milky Way has interacted with other galaxies in the past. The Sagittarius dwarf galaxy was torn apart by the Milky Way's gravitational pull and absorbed into it. This interaction changed the structure of the Milky Way, and perhaps also affected the orbit of our solar system. Now let's look beyond our galaxy at the Milky Way's neighbors. The Milky Way is not alone. It is a member of a galaxy family called the Local Group, together with more than approximately 50 galaxies. The vast majority of these are very small, dwarf galaxies. The two main big players are the Milky Way and the Andromeda Galaxy. Andromeda is about twice the size of the Milky Way, approximately 2.5 million light-years away, and it is currently approaching us at approximately 110 kilometers per second. This may seem slow, but when the distance is this large, the result is inevitable. In approximately 4.5 billion years, Andromeda and the Milky Way will collide. More precisely, they will merge, because galactic collisions are actually the passage of two galaxies through each other and their eventual merger. Stars don't collide with each other, because the distances between stars are so large that even as two galaxies pass through each other, star collisions are extremely rare. But what happens during this merger? Gravitational interactions intensify incredibly. Some stars are flung outside the galaxy. Gas clouds are compressed and enormous bursts of star formation occur. The central black holes of both galaxies approach each other and eventually merge. A much larger black hole forms. What happens to the solar system during this merger? Most likely, the solar system will preserve its integrity. The distances between stars are so large that it is extremely unlikely that Andromeda stars will directly threaten our solar system. But the solar system's orbit within the galaxy may change. We may be transported to a new region, perhaps a denser and more dangerous region, or perhaps the exact opposite. We may be flung to the outer regions of the merging galaxies, to a much calmer and more isolated position. This uncertainty is both unsettling and fascinating. Now let's come to the deepest point of this section. The question of what's above the solar system at this point arrives at this answer. The galaxy is there. And this galaxy is an extremely dynamic, extremely complex, and extremely interesting structure. But the galaxy is not just a beautiful object to look at from the outside. The galaxy is an active environment that shapes the fate of every system living within it. The black hole at the galactic center manages the dynamics of the entire galaxy. The spiral arms-shaped star formation. The galactic halo holds the majority of the galaxy's mass invisibly. And within this picture, the solar system orbits in a relatively calm point within the galactic habitable zone between the spiral arms. This position may not be coincidence, or it may be coincidence, but as a result of this coincidence, complex life on Earth was possible for billions of years. And that complex life eventually produced beings who look up at the sky and ask all these questions. Right now, on a small planet orbiting one of the 200 to 400 billion stars of the Milky Way, 26,000 light-years from the monster at the center of the galaxy, in a calm region between the spiral arms, inside the local bubble, at a point in the middle of the journey toward merger with Andromeda, you are here. And you can think about all of this context, all of these coordinates, all of this reality. This is a small but extremely rare thing. In the next section, we'll move beyond the galaxy. We'll look at the local group, galaxy clusters, superclusters, and the largest structures in the observable universe. We'll take the question of what's above the solar system to a truly universal dimension. Because above the solar system, there isn't just the galaxy. Above the galaxy, there are things too. And those things are the largest structures ever observed. Now close your eyes, rest, and think about this. Right now, you are 26,000 light-years from the supermassive black hole that is the center of the Milky Way. The energy released from that black hole set out 26,000 years ago and has not yet reached you. Not yet. The galaxy is large, very large, and you are inside it. Step outside the galaxy, just for a moment. In your mind, rise up from Earth, pass through the atmosphere, pass through the solar system, pass through the Oort cloud, pass through interstellar space, pass through the disk of the Milky Way, pass through the galactic halo, and now stop. Look back. You can see the Milky Way from the outside, with its spiral arms, with the bulge at its center, with its width of hundreds of thousands of light years. And around it, at close distances, there are other galaxies. These galaxies are not alone, gravitationally bound to one another, moving together, forming a structure together. And this structure is the next answer to the question of what lies above the solar system. In this section, I'm going to tell you the following. What lies beyond the Milky Way, the local group, galaxy clusters, superclusters, and the largest structures in the observable universe, and where our solar system stands within these structures. Because above the solar system, there isn't just the galaxy. Above the galaxy, there is much more. And these things are the largest, most complex, and most fascinating structures ever observed. Let's start with the local group. The Milky Way is not a solitary galaxy in space. Together with more than approximately 50 galaxies, it is a member of a galaxy family called the local group. The two largest members of this family are the Milky Way and Andromeda. The vast majority of the rest are dwarf galaxies, small, irregular, or elliptical structures. The total diameter of the local group is approximately 10 million light-years. This figure is approximately 100 times the Milky Way's own diameter. Think about that. The Milky Way is this large, and the local group is 100 times larger than the Milky Way. And the local group is the smallest of the structures we're in. Let's look at the important members of the local group. The Andromeda Galaxy, also known as M31, the largest neighbor of the Milky Way, approximately 2.5 million light-years away, larger than the Milky Way. It is estimated to contain approximately 1 trillion stars, and it is approaching us at approximately 110 kilometers per second. This speed is unimaginably large, but the distance is also unimaginably large. So this approach will result in a merger approximately 4.5 billion years from now. But Andromeda is not only coming toward us. Andromeda itself has satellites. Two dwarf galaxies named M32 and M110 orbit around Andromeda. And these satellite galaxies will also interact with the Milky Way during the merger process. The Triangulum Galaxy, also known as M33, the third largest member of the local group, approximately 2.7 million light-years away, contains approximately 40 billion stars, spiral in structure but without a prominent bulge at its center. And recent research suggests that Triangulum may actually be a satellite galaxy orbiting Andromeda in a large orbit. The satellites of the Milky Way, the Large Magellanic Cloud and the Small Magellanic Cloud. These two irregular dwarf galaxies are extremely close to the Milky Way. The Large Magellanic Cloud is approximately 160,000 light-years away. The Small Magellanic Cloud is approximately 200,000 light-years away. Both are visible with the naked eye. When viewed from the southern hemisphere, they appear as bright cloud-like patches in the sky. Both of these galaxies are being shaped by the Milky Way's gravitational pull. The Milky Way is slowly drawing them in. Billions of years from now, these galaxies too will merge with the Milky Way. And this merger process has already begun. A vast bridge of gas and stars extending from the Large Magellanic Cloud reaches toward the Milky Way. This structure, called the Magellanic Stream, is concrete evidence of the gravitational dance between the two galaxies. Now let's move beyond the local group. The local group seems large on its own, but on a universal scale it is extremely small, because the local group is a tiny part of a much larger structure. The Virgo supercluster. The local group, along with the surrounding galaxy clusters and groups, forms a larger structure called the Virgo supercluster. The diameter of this supercluster is approximately 110 million light-years, and it contains approximately 100 galaxy groups and clusters. At the center of this supercluster sits the Virgo galaxy cluster, approximately 65 million light-years away. It contains more than 1,300 galaxies. And at the center of this cluster is a giant elliptical galaxy called M87. M87 made history in 2019 because it was the galaxy in which humanity first photographed the shadow of a black hole. That iconic orange and black image, the shadow of that enormous black hole. All galaxies are being drawn toward the center of the Virgo cluster and thus toward the center of the Virgo supercluster by gravitational attraction, including the Milky Way. The center creating this pull is called the Virgo cluster itself, but there is also a larger gravitational center. The Great Attractor. The Great Attractor. Even this name alone is fascinating, and the reality is as dramatic as the name. In the late 1970s and early 1980s, astronomers noticed something strange. It was known that the Milky Way was being pulled toward the Virgo cluster. But when the movement expected from the expansion of the universe was calculated, it was impossible to fully explain this movement. There was something more powerful, something larger, and this thing was hiding in a specific region of the southern sky, in the direction of the constellations Centaurus and Hydra. But this region is behind the galactic plane. That is, the Milky Way's own stars, gas, and dust make this region invisible. This is called the zone of avoidance. You want to look outside the Milky Way, but you're standing in the middle of your own galaxy and the galaxy's own matter blocks the view in certain directions. However, radio telescopes and infrared observations partially managed to overcome this obstacle. And in that region, a massive galaxy cluster was discovered, the Norma cluster. Then an even larger structure of which this cluster was a part was seen, the Shapley supercluster. The Great Attractor is most likely the combined gravitational effect of this Shapley supercluster, approximately 250 million light-years away, unimaginably large in mass. And this gravitational pull is drawing all galaxies in the Virgo supercluster, including the Milky Way, at approximately 600 kilometers per second in that direction. 600 kilometers per second. 1,750 times faster than sound. At this tremendous speed, independent of the expansion of the universe, we are constantly moving toward the Great Attractor. And it took us a very long time to realize this, because the zone of avoidance was hiding this movement. Now let's move to an even larger structure. In 2014, a very important discovery was made. One of the largest maps in the history of astronomy was completed, and this map showed that the Virgo supercluster was actually a tiny part of a much larger structure. The name of this structure is Laniakea. It means immeasurable heaven in Hawaiian. The Laniakea supercluster is an enormous structure approximately 500 million light-years wide. It contains approximately 100,000 galaxies. Its total mass is equivalent to approximately 100 million billion solar masses. And the Milky Way is located on the edge of this enormous structure, in a small arm. The team that discovered Laniakea mapped the velocity fields of galaxies. Like water in a basin, galaxies flow in the direction of gravitational attraction. By following these flows, they brought together galaxies sharing a common gravitational basin. And when they drew the boundaries of this basin, Laniakea emerged. The Milky Way is not toward the center of Laniakea, but in the outer region of Laniakea, on its edge. And this raises an interesting question. In the large-scale structure of the universe, if galaxies form such enormous structures, what are the voids outside these structures? And the answer to this question reveals one of the universe's most astonishing realities. Cosmic voids. We said galaxies cluster in these enormous structures. Superclusters, clusters, groups, galactic filaments. But what is between these structures? Almost nothing. Cosmic voids are enormous, almost completely empty regions stretching between galaxy filaments and walls. The sizes of these voids are incredible. The Boötes void is approximately 330 million light-years in diameter. In a volume this large, there are almost no galaxies, just a few, inside almost completely empty. And these voids are the fundamental components of the universe's large-scale structure. Because when viewed from sufficiently far away, the universe shows a foam or sponge structure. Filaments and walls form the thick walls of the foam. The voids form the air bubbles of the foam. This structure is called the cosmic web or large-scale structure. And the formation of this structure is the product of a process that has continued since the first moments of the universe. Right after the Big Bang, the universe had an extremely homogeneous structure, everywhere at approximately the same density, but not exactly homogeneous. There were very small density differences arising from quantum fluctuations, and these small differences grew under the influence of gravity. Denser regions attracted more matter. Less dense regions emptied out further. And this process continued for billions of years. Result: the enormous filament network and enormous voids we see today. And now let's come to a very fascinating reality. This large-scale structure overlaps with patterns in the cosmic microwave background radiation. That is, the cosmic microwave background radiation is the remnant of light emitted approximately 380,000 years after the Big Bang. And the very small temperature differences in this light contain the seeds of today's large-scale structure. In other words, the origins of the largest structures we see in the universe lie in events that occurred at the quantum scale in the first moments of the universe. Without quantum uncertainty, there would have been no these density differences. Without these density differences, galaxies would not have formed. Without galaxies, stars would not have formed. Without stars, planets would not have formed. And you would not be here. You are the product of a small vibration created by quantum uncertainty billions of years ago. This thought makes you feel both small and large at the same time. Now let's look at the boundaries of the observable universe. The observable universe is bounded by the maximum distance light can travel from us on Earth. The universe is 13.8 billion years old. But the universe is also expanding. So the radius of the observable universe is not just 13.8 billion light-years. Taking expansion into account, the radius of the observable universe is approximately 46.5 billion light-years. And in this sphere, there are trillions of galaxies. But the observable universe is not the entirety of the real universe. Probably just a small piece of it. We don't know the boundaries of the real universe. Nor can we, because the light from those boundaries has not yet reached us. And because the universe is expanding, perhaps it never will. This thought is mind-bending. Everything we can observe is perhaps a tiny portion of the real universe. And we are on the fourth rocky planet of a tiny star system on the edge of a tiny galaxy inside this tiny portion. Now let's come to the most important point of this section. We asked what lies above the solar system. And in this section, we answered this question from a very broad perspective. There is the local group, with Andromeda, the Milky Way, and dozens of dwarf galaxies inside, approximately 10 million light-years wide. There is the Virgo supercluster, a larger structure containing the local group, 110 million light-years wide, containing approximately 100 galaxy groups and clusters. There is the Great Attractor, the enormous gravitational center pulling all these structures toward itself at 600 kilometers per second. There is the Laniakea supercluster, 500 million light-years wide, a giant structure containing 100,000 galaxies. The Milky Way is on its edge. There are cosmic filaments and voids, the largest scale structure of the universe. Filaments extending billions of light-years and the enormous voids between them. And beyond all of these is the observable universe, with a radius of 46.5 billion light-years, containing trillions of galaxies. And beyond all of these is a universe we cannot yet see, whose boundaries we don't know, perhaps infinite, perhaps finite but unimaginably large. Within this picture, where is the solar system? On the edge of Laniakea, in the outer region of the Virgo supercluster, inside the local group, in the middle region of the Milky Way, in the Orion Arm, in the local bubble, inside the Oort cloud. And the only being that can hold all of these coordinates in mind at the same time is, most likely, someone like you watching this video right now. This thought is both unsettling and fascinating. Unsettling because the scale is unimaginably large. Within this vastness, the solar system is an invisible point. The Milky Way is an invisible point. Even Laniakea is an invisible point. Fascinating because inside this point, inside this unimaginably small point, there is a consciousness capable of grasping, understanding, and questioning all this vastness. Perhaps this is the universe's way of becoming aware of itself. The universe produced trillions of galaxies, quadrillions of stars, quintillions of planets, and almost none of them are aware that they exist. They just exist. Chemical reactions work. The laws of physics operate, but there is no awareness. And then, perhaps through the coming together of extremely rare conditions throughout the history of the universe, consciousness emerged in certain places. And that consciousness turned back, looked at the universe, and asked, "Where am I?" Right now, you're doing exactly this. And this may be the deepest answer to the question of what lies above the solar system. Above, there aren't just galaxies and superclusters and filaments. Above, within all these structures, lies the answer to why awareness is so rare and so precious. In the next section, we'll take this great picture in a completely different direction. We'll talk about the universe's future, dark energy, and where all these enormous structures are ultimately headed. Because the universe is not just large. The universe is moving, changing, and one day, the vast majority of the magnificent structures we see today will disappear from our observable universe, with a constantly accelerating expansion. And this reality shows in a very different way how precious existence is. Now close your eyes, rest, and think about this. Right now, you are on the edge of Laniakea, on the edge of a structure 500 million light-years wide containing 100,000 galaxies. And this structure is sliding toward the Great Attractor at 600 kilometers per second. And you are sliding with it. Stop. Feel this. 600 kilometers per second. Right now, at this very moment. And you can feel it. The universe is becoming lonely. This sentence is not a metaphor. It is real. Right now, at this very moment, the universe is expanding. Every second, every minute, every year, galaxies are moving away from each other. Distant galaxy clusters are moving away ever faster. And the speed of this movement is increasing. That is, the universe is not just expanding. It is expanding at an ever-increasing rate. And behind this acceleration lies one of physics' greatest mysteries: dark energy. In this section, I'm going to tell you the following: the future of the universe, what dark energy is and how it shapes the fate of the universe, what will happen to Laniakea, the Virgo supercluster, the local group, and ultimately the Milky Way within this picture, and how this future will transform the space above the solar system. Because the question of what lies above the solar system is not only valid for today. This space is changing, transforming, and in billions of years, it will become unrecognizable. First, we need to understand the story of dark energy. 1998. Two independent astronomy teams were researching something very different. They were trying to measure how the rate of expansion of the universe was changing. To do this, they use type Ia supernova explosions. These types of supernova explosions are objects known as standard candles. That is, they always explode with the same brightness. This property makes them perfect tools for measuring distance. If you measure how dim a type Ia supernova appears, you can calculate how far away it is. Both teams expected to find the same thing, that the expansion of the universe was slowing down, because the Big Bang had given a powerful start, but gravity was expected to break this expansion, just like a stone thrown upward slowing down. But what they found was the exact opposite. The expansion of the universe was not slowing down. It was accelerating. This discovery was so surprising that initially both teams questioned their own data. They thought there was an error. They redid the analysis, checked with different methods, but the result didn't change. The expansion of the universe was accelerating. And to explain this acceleration, there would need to be a form of energy existing in empty space itself, pushing this expansion outward. This form of energy was named dark energy. This discovery was awarded the Nobel Prize in Physics in 2011. Saul Perlmutter, Brian Schmidt, and Adam Rees shared this prize. But equally important as the prize is this. Dark energy makes up approximately 68% of the universe's total energy content. Dark matter is 27%. Everything we see, stars, galaxies, planets, atoms, light, everything, makes up only 5% of the universe. 5%. And we are inside that 5%. We don't even know what the remaining 95% is. What is dark energy? The honest answer, we don't know. We really don't know. According to one hypothesis, dark energy is the energy of empty space. According to quantum mechanics, empty space is not truly empty. Inside it, virtual particle pairs are constantly being created and annihilated. And these quantum fluctuations give space itself an energy density. This energy is called the cosmological constant. Einstein added this term to his general relativity equations, then called it his greatest mistake and removed it, but perhaps he was right after all. According to another hypothesis, dark energy is not constant. Dynamic. It changes over time. Perhaps it is increasing, perhaps decreasing. In this case, the fate of the universe could go in very different directions. And there is a third possibility. Perhaps there is no such thing as dark energy. Perhaps the general theory of relativity behaves in unexpected ways at very large scales. Perhaps we need to revise the theory. Which is correct? We don't know. And this not knowing is one of the greatest open questions of modern physics. But we know, or at least can estimate, what the existence of dark energy means for the future of the universe. Now let's look at the possible futures of the universe. First scenario, Big Freeze. This is the scenario most consistent with current observations. If dark energy remains constant, the expansion of the universe continues forever. And this expansion accelerates ever further. What happens first? Galaxies beyond the local group move away ever faster. The Virgo cluster, the Shapley supercluster, most of Laniakea. All of them eventually leave our observable universe. Their light can no longer reach us, as if they never existed. Approximately 100 billion years from now, all galaxies beyond the local group will have retreated from our observable universe. At that point, if there were observers of a still existing civilization, they would see in the sky only the merged Milky Way and Andromeda galaxy called Milkomeda, and a few satellite galaxies. The universe would look empty, a vast, dark space with almost nothing in it. This point is extremely important. If an intelligent civilization hadn't existed until this period, what would it see when it looked at the sky? A single galaxy, its own galaxy, and darkness. Endless darkness. There would be no observational clues to understand that the universe is expanding, that other galaxies exist, that the Big Bang occurred. This thought is extremely unsettling. We are very fortunate. We are living in this early period of the universe. We can still see thousands of galaxies. We can still detect the cosmic microwave background radiation. We can still read the history of the universe. Any civilization born 100 billion years from now will not have this opportunity. Let's continue. What happens after 100 billion years? Stars age and die. The gas clouds needed for new star formation are depleted. Gas in galaxies gradually decreases. New stars are no longer born. Existing stars complete their lifetimes. Large stars transform into black holes or neutron stars. Medium-sized stars transform into white dwarfs. Small red dwarfs are extremely long-lived. They can continue burning for trillions of years, but eventually they too will go dark. Approximately 10 to the power of 14 years from now, a duration about 10 million times the current age of the universe, the last star will have gone dark. Galaxies will have turned into collections of dark and cold stellar remnants. White dwarfs, neutron stars, black holes. This period is called the Dark Age, the cosmological Dark Age, and this age continues even after. Black holes persist, but they too are not permanent. A quantum mechanism called Hawking radiation causes black holes to evaporate, albeit very slowly. This process takes unimaginably long, a billion years. But eventually, even the largest black holes evaporate. And what remains? Photons, neutrinos, electrons, and positrons, all of them, in an ever sparser space, in an ever colder universe, drifting toward infinity. This is the Big Freeze, the thermodynamic death of the universe. The final equilibrium where everything reaches maximum entropy. Second scenario, Big Rip. This scenario occurs when dark energy is not constant but increases over time. If dark energy is strengthening, the rate of expansion of space eventually exceeds even the speed of light. And at this point, expansion would tear apart not just the space between galaxies, but the space inside galaxies, star systems, planets, and atoms. Everything is torn apart, literally. In this scenario, the final moments are dramatic. Approximately 60 million years before the Big Rip, galaxy clusters begin to disperse. 3 months before, the solar system disintegrates. 30 minutes before, stars disintegrate. 10 to the power of minus 19 seconds before, atoms disintegrate. And then everything ends. Third scenario, Big Crunch. This scenario occurs when dark energy weakens over time and gravity ultimately prevails. The expansion of the universe slows, stops, and reverses. Galaxies start accelerating toward one another. Temperature increases. Stars explode. All matter and energy collect again at a single point. In a sense, the reverse of the Big Bang, or perhaps the beginning of a new Big Bang. Current data does not support this scenario, but it has not been completely ruled out either. Now, independent of these scenarios, let's look at what will happen in the nearer future. Let's withdraw from this distant future of the universe and return to the billions of years scale. In approximately 4 to 5 billion years, the Sun will enter the red giant phase. This is the period when the Sun's outer layers swell and expand. The Sun will grow so large that it will swallow Mercury, Venus, and probably Earth. The oceans will evaporate. The atmosphere will disappear. Earth's surface will melt. By this point, if humanity still exists, it will have long since migrated to other star systems, or at least to more suitable locations within the solar system, perhaps to Mars, perhaps to Jupiter's moon Europa, perhaps to entirely artificial habitats. But long before that date, other things will happen too. In approximately 4.5 billion years, as we discussed earlier, the Andromeda Galaxy will begin to merge with the Milky Way. This process will take millions of years. The first passage will occur. Then the galaxies will move apart, then merge again, and finally merge into a single galaxy. This new galaxy is being called Milkomeda. It will most likely be a large elliptical galaxy. The spiral arms will disappear. The solar system will most likely continue orbiting in a new orbit, in a new position. There may be close passes from Andromeda stars, but the probability of a direct collision is still very low. So how does this merger process change the space above the solar system? It changes it dramatically. Right now, the solar system is in a relatively calm, relatively isolated region of the Milky Way. The density of nearby stars is low. Dangerous interactions are rare. This is an important factor that has allowed complex life on Earth to remain stable for billions of years. But during the merger with Andromeda, the structure of the galaxy will change fundamentally. Star density may increase. Gravitational interactions may intensify. New star-forming regions may emerge. And these changes will completely transform the environment around the solar system, the space above the solar system. What the space above the solar system will look like during that period is very difficult to predict from today, because the merger process is chaotic and hard to predict. Now let's come to a much less discussed but extremely interesting topic. The expansion of the universe is affecting not just distant galaxies, but us too, but in different ways. At a local scale, gravitationally bound systems are not affected by the expansion of the universe. Earth orbits the Sun, and this orbit is independent of the universe's expansion. The solar system orbits within the Milky Way, also independent of expansion. The Milky Way is within the local group, also independent, because gravitational bonding is stronger than the pushing force of dark energy. At these scales, but at sufficiently large scales, dark energy prevails. Galaxies outside the Virgo cluster are moving away. Most of Laniakea will eventually disperse. Now think about this. Laniakea contains 100,000 galaxies, we said. All of these galaxies are currently sharing the same gravitational basin. But this unity is not permanent. Dark energy will break apart this basin. Galaxies will be drawn to their own local groups, and those without sufficient gravitational bonds will drift off into the void. This is a concrete image of cosmic loneliness. Now let's address this loneliness from a much more personal perspective. Right now, when you look at the sky, you can see galaxies billions of light years away. The James Webb Space Telescope has captured images of galaxies 13 billion light years away. We can look all the way back to nearly the beginning of the universe. This is an incredible privilege, but this privilege is not permanent. Any observer from a civilization existing 100 billion years from now will not be able to see even neighboring galaxies. Everything outside the local group will have been pulled beyond the horizon by dark energy. The history of the universe will have become unreadable. The cosmic microwave background radiation will have cooled and dispersed so much that it can't be detected. The evidence of the Big Bang will be invisible. Those observers, if they existed, would never know how the universe began. They would only see their own galaxy, and would think that the universe had always existed this way. But we are living in the unique window where we can still have this knowledge. Before this window closes, now let's come to the most philosophical point of this section. In this section, we addressed the question of what's above the solar system with a temporal dimension. What will happen in the future? And how different is this future from today's picture? The answer, incredibly different. Right now, above the solar system, there is the Oort cloud, interstellar space, the local bubble, the Milky Way, the local group, the Virgo supercluster, Laniakea, cosmic filaments, and 2 trillion galaxies. Billions of years from now, the vast majority of these will have either changed, transformed, or retreated from our observable universe. Trillions of years from now, the last stars will have gone dark. Galaxies will have turned into dark collections of stellar remnants. And in an even more distant future, even black holes will have evaporated. This picture is both unsettling and astonishingly liberating. Unsettling because it shows that everything is temporary. Even the largest structures are not permanent. Laniakea is not permanent. The Milky Way is not permanent. The Sun is not permanent. Earth is not permanent. Liberating because this transience makes the value of the present moment infinitely greater. Things that are transient are incredibly precious in the moment they exist. And right now you are existing. And you are living this moment in the very middle of all these enormous structures of the universe. In this section we talked about dark energy, the accelerating expansion of the universe, the big freeze and big rip scenarios. We talked about how the Andromeda merger will transform the space above the solar system. And we saw how these changes will transform all the structures above the solar system over billions of years. But this is not the most important thing. The most important thing is this: within all these changes, all these transformations, all this transience, right now to exist and to be aware of all of this is an extremely rare thing. The universe existed, matter formed, stars burned, planets shaped, life began, and finally, a consciousness capable of being aware of all this process emerged. And this consciousness right now is asking what lies above the solar system. And the answer is, everything is there, both the present and the past and the future, both small and large, both transient and lasting, both knowable and mysterious, all there, all real, all in constant interaction with you. And right now, when you look at this night, every point of light you see in that darkness is a part of this story. In the next and final section, we'll bring all of this journey together. We'll talk about what this enormous journey from the Oort cloud to Laniakea, from there to the future of the universe, tells us, and we'll understand how this incredible, vast, complex space above the solar system makes you feel both small and large. Because this journey is not just outward, it is also inward. Now close your eyes, rest, and think about this. Right now, the solar system is traveling at 220 kilometers per second around the center of the galaxy. This galaxy is sliding toward the Great Attractor at 600 kilometers per second. And in the midst of all this movement on a planet, a being is aware of all of this. That being is you. And this awareness may be the rarest and most precious event in the universe. Now look up. There's a ceiling, maybe the sky, maybe clouds, maybe stars. And everything you've learned since the beginning of this video has completely changed how you look at that upward gaze. Because now you know, up there there's not just darkness. Up there there's not just stars. Up there there's an incredibly complex, incredibly vast, incredibly active reality. And tonight, at the end of this journey, it's time to bring all of this together. In this section, I'm going to tell you the following: what everything we've seen throughout this journey truly means, how the enormous space above the solar system makes you feel both how small and how large you are, and why, within this vastness, looking at this night, this silence, this darkness, is one of the deepest experiences of human existence. Because this video is not just information, not just numbers, not just structures and distances. This video is an invitation to reconnect with the universe. First, let's review the journey we made one more time, but this time not with numbers, with feeling. We started from just outside the solar system. We saw the heliosphere, that enormous magnetic bubble created by the sun, the invisible shield blocking harmful cosmic rays and interstellar winds. We are inside it. Our sun wraps us in this bubble, protects us. Then we entered the Oort cloud, the true boundary of the solar system, trillions of masses of ice and rock, extending a small fraction of a light year from the sun. enveloping the sun in a spherical cloud. These masses have been there for billions of years, remnants left over from the formation of the solar system. And occasionally, under the influence of galactic tides, they let go of their orbits and begin their long journeys toward the sun. We call them comets. They glide through the sky for thousands of years. Throughout all of human history, we looked at them, considered them omens, considered them messengers of the gods. But they are just travelers billions of years old, coming from the Oort cloud. Then we entered the local bubble. We live inside that giant balloon left by the series of supernovae that exploded in this region millions of years ago. This balloon offers us a sparse environment, lower interstellar matter density, a stronger heliosphere, better cosmic ray protection. In a sense, those ancient supernova explosions prepared a home for us. Then we looked at the Milky Way. We saw that monster, the black hole with a mass of 4 million suns at the center of our galaxy. And we understood that we are 26,000 light-years away from that center, in a quiet corner between the spiral arms, in the galactic habitable zone, at sufficient distance from both center and edge. This position allowed complex life to maintain its stability for billions of years. Then we moved even further out. We saw the local group. We saw Andromeda, that enormous spiral galaxy, and we learned that it will merge with the Milky Way in 4.5 billion years. This merger will completely transform the space above the solar system. But the solar system will most likely preserve its integrity. And in that merged galaxy, it will continue orbiting in a new orbit in a new region. Then we discovered Laniakea, that giant supercluster 500 million light-years wide containing 100,000 galaxies. And we learned that the Milky Way is located on the edge of this enormous structure in a small arm, and that the entirety of this structure is sliding toward the Great Attractor at 600 kilometers per second. Then we talked about dark energy, the accelerating expansion of the universe, and how this expansion will transform, fragment, and ultimately lead the universe toward thermodynamic death over billions of years. This journey was not just through space. It was also through time, from the past to the future, from the first supernova explosions to the final moments of the universe. And now, after all this journey, I want to ask this question. How did this knowledge change you? Because knowledge alone is not enough. Knowledge needs to sink in. Knowledge needs to be felt. And this feeling most often contains two opposite emotions at the same time: smallness and greatness. Smallness comes from here. We saw that the solar system orbits one of billions of stars in the Milky Way. The Milky Way is a small member within the local group. The local group is a small piece of the Virgo supercluster. The Virgo supercluster is a small piece of Laniakea. Laniakea is just one of the structures in the observable universe containing 2 trillion galaxies. And the observable universe is probably a tiny fragment of the real universe. Within this scale, Earth is smaller than a grain of sand. You are as small as an atom on that grain of sand. And this thought creates an incredible feeling of smallness. But then something else comes: greatness. You can think about this scale. You can grasp these distances. You can visualize these structures in your mind. Laniakea, dark energy, the big freeze, the Oort cloud. You carry a consciousness capable of understanding, questioning, and feeling all of these. And this consciousness is an extremely rare thing in this universe. The vast majority of the universe is not aware that it exists. Stars are burning. Black holes are swallowing matter. Galaxies are merging. Cosmic filaments are forming. All of this is happening, but there is no evidence that any of it is aware of it. Awareness is the rarest and most mysterious property of matter. And you have this awareness. This makes you both small and large. At the same time, two sides of the same reality. Now I want to share the most important thing this journey taught me. The question of what lies above the solar system is really asking another question. Where are we? And the answer to this question does not consist only of coordinates. Yes, we are on the edge of Laniakea. Yes, we are in the Orion arm of the Milky Way. Yes, we are 26,000 light-years from the galactic center. These coordinates are correct. But these coordinates form only the skeleton of the true answer. The true answer is this: we are at a point where the universe is trying to understand itself. The universe expanded for 13.8 billion years. Stars formed and died. Elements were synthesized. Planets took shape. Chemistry enriched. And at the end of this long process, through the perfect coming together of certain conditions, life emerged in certain places. And that life grew more complex over time. And that complexity gave birth to consciousness over time. And that consciousness looked up at the sky over time and asked, "What is up there?" This question is the question the universe is asking itself. And as beings who ask this question, we are a part of the universe. We are not observers outside it looking at it. We are inside the universe. We are made of the universe's material. And something made of the universe's material is understanding the universe. This thought is both philosophical and extremely real, because every atom in your body was once inside a star. Atoms synthesized by fusion inside a previous generation star, existing before the solar system formed. And when that star died, it scattered these atoms into space. They wandered in space. They were gathered when the solar system formed. They settled on Earth. They mixed into the ocean. They entered a cell. They evolved for billions of years. And finally, they became you. You are the recycled stardust of the Milky Way. And right now, part of that stardust is looking at the Milky Way and understanding it. The beauty of this cycle exists in nothing else in the universe. Now let's return to what the space above the solar system truly means, with this thought in mind. That space is not just empty space. That space is the stage of an evolutionary process spanning billions of years. Every structure, every filament, every galaxy, every star cluster is a part of this stage. And every part of this stage has a direct or indirect role in your being able to exist. Without the Oort cloud, the solar system could have been seriously disturbed by external influences much earlier. Without the local bubble, cosmic ray bombardment would have been much more intense. Without the galactic habitable zone, the solar system would have formed either in a very dangerous or a very impoverished environment. Without Andromeda, perhaps the Milky Way's galactic evolutionary history would have been very different. Everything is connected to each other. And this connection is not just gravitational. It is chemical, temporal, evolutionary, and perhaps most deeply experiential. Now let's come to the last and deepest point of this journey. Throughout this video, we answered the question of what lies above the solar system like this. There is the heliosphere. There is the Oort cloud. There is interstellar space. There is the local bubble. There is the Milky Way. There is the black hole at the galactic center. There is the local group. There is Andromeda. There is the Virgo supercluster. There is the Great Attractor. There is Laniakea. There are cosmic filaments. There are cosmic voids. There is the observable universe. And beyond it, the real universe we cannot see but believe exists. But now I want to give you a different answer. What lies above the solar system? There is a question, and there is a consciousness asking that question. And these two, within this enormous picture, are perhaps the rarest and most precious things. The universe produced matter and energy for 13.8 billion years. But producing questions is much harder. To produce questions, first consciousness is needed. And for consciousness, matter needs to reach an incredibly complex organization. And this organization requires incredibly rare conditions to come together. Right now, at this very moment, you are the product of these rare conditions. And these rare conditions came together in the very midst of that enormous space above the solar system. The right galaxy, the right galactic region, the right star, the right planet, the right chemistry, the right time. The coming together of all of these at the same time is an unimaginably small probability. But it happened, and the result was you. And you, right now, are asking this question. Is this coincidence? Perhaps. Or perhaps the universe being so vast makes the realization of such low probabilities inevitable. In trillions of planets, trillions of different conditions may have been tried. And in a small fraction of these conditions, consciousness may have emerged. We are one example of that small fraction. But this probabilistic explanation does not diminish the magnitude of the experience. On the contrary, it increases it. Because think about this. This moment, the moment you are asking these questions, has never happened before in the 13.8 billion year history of the universe. You thinking exactly these thoughts at exactly this moment is happening for the first and perhaps last time in the universe's 13.8 billion year history. This moment will not repeat. And this reality is both heavy and lightning. Heavy because it reminds us of transience. You, the sun, the Milky Way, Laniakea, all transient. Lightning because this transience makes the value of the present moment infinitely precious. Transient things are incredibly valuable in the moment they exist. And right now you are existing. And you are living this moment in the very middle of all the enormous structures of the universe. Now I want to name the feeling you may have felt while watching this video. Oh, there is no exact equivalent in Turkish. Perhaps husu, reverence. But it's more. Both fear and admiration. Both smallness and connection. Both weight and freedom. This feeling is the feeling humanity has always felt when looking up at the sky throughout its existence. And this feeling is not in vain. This feeling is telling you something, making a reminder. You are a part of this universe. And this universe is far larger, far more complex, far more beautiful than you imagined. We asked what lies above the solar system. And the answer was an incredible picture extending from the Oort cloud to Laniakea. But the most important detail of this picture is the reality that you are the one looking at it. Because the picture is not complete without the one who looks. The solar system exists. The galaxy exists. The universe exists. But if there is no one to see, understand, feel, and question these things, this picture has something missing. You are completing that missing piece. And this is not a small thing. Perhaps the greatest miracle of the universe is that it has been able to become aware of itself. And this awareness, on a small planet orbiting one of trillions of stars, emerged at the end of an evolutionary process spanning billions of years. We are the carriers of that awareness. And this responsibility is both heavy and honorable. Now return to this night, to where you are, to this sound, to this silence, and look up. Do you know what's up there now? There is the Oort cloud, trillions of masses of ice, silently orbiting the sun for billions of years. No one seeing them, no one knowing them. There is the local bubble, the home left by stars that exploded millions of years ago, the legacy of the explosions that surrounded, protected, and created us. There is interstellar space, with cosmic rays and organic molecules inside it. Perhaps the seeds of life, particles floating throughout the galaxy, perhaps one day seeding or already having seeded life on another planet. There is the Milky Way, that giant spiral structure of 200 to 400 billion stars, a monster at its center and us on its edge. There is Andromeda, 2.5 million light-years away, approaching toward us. It will be here in 4.5 billion years. And that merger will change the entire picture above the solar system. There is Laniakea, the gravitational dance of 100,000 galaxies. And we are on the edge of that dance with a small step. There is dark energy, invisible, incomprehensible, but determining the fate of the universe. Every second, every millisecond, moving everything a little further apart from everything else. And beyond all of these, there is the real universe that we cannot see but can sense, whose boundaries we don't know, perhaps infinite, perhaps finite but unimaginably large. All of this is up there, right now, tonight, above you, and you are aware of it. This awareness is a greater miracle than the existence of the Oort cloud, a more important discovery than the discovery of dark energy, a more meaningful achievement than the mapping of Laniakea. Because all these discoveries, all these maps, all these calculations ultimately come back to you and gain meaning in you. Sleep now. Rest. Tonight above your head there is the Oort cloud. Around you there is the local bubble. Below and above you the Milky Way extends. Hundreds of millions of light years away the edges of Laniakea fade from view. And far beyond all of these, there are galaxies whose light has not yet reached you. Structures about whose existence you can never have information. But you are here, and tonight you sleep with this knowledge. And this knowledge will be there when you wake up in the morning. The space above the solar system is the same during the day. The Oort cloud is there during the day too. Laniakea is sliding during the day too. Dark energy is pushing during the day too. Only the sky brightens, and stars become invisible. But they are there, always there. You are there too. And this, considering how large the universe is an unimaginably small reality. But the most important reality. Good night, hands. Perhaps. Now return to this night, to where you are, to this sound, to this silence. And look at that sky out there. Every star carries a threat. Every corner holds a risk. The universe is hostile. The universe is dangerous. The universe seems almost specially designed to make intelligent life difficult. But right now, at this very moment, you are here. You are asking these questions. You have this awareness. And this awareness may be one of the rarest events in the history of the universe. In the next and final section, we will bring all of this story together. Moving beyond the great filter, we will talk about what humanity needs to do in the face of this silence. Because this story does not end in despair, but in awareness. And that awareness may be enough to change the universe. Now close your eyes. Rest. The universe is dangerous, but you are here, and that may change everything. Tonight, look at the sky. From where you are, from your window or your balcony, or simply picturing that moment somewhere deep in your mind. Look at the sky. There are stars, glowing points, each one actually a sun, each one a vast, blazing, colossal sphere of plasma. And the darkness between them, that darkness is what we have been discussing since the beginning of this video. But now, thinking of all the sections together, that darkness looks different, deeper, heavier, more meaningful. We have talked about a great many things up to this point. We saw the Fermi paradox. We understood the great filter. We examined the disappearance of knowledge. We explored the physical dangers of the universe. And we saw that the silence of the universe stems not merely from the absence of civilizations, but from a far deeper and far more complex set of processes. Now it is time to bring all of this together. What does this silence mean? And what does this meaning say to humanity? First, honesty is required. Science cannot give a definitive answer to this question. The great filter is not a proven fact. The universe's silence has no single explanation. Perhaps civilizations are very rare. Perhaps technological barriers are greater than expected. Perhaps our detection methods are insufficient. Perhaps there are very different forms of communication and we are looking at the wrong things. But this also needs to be said. Scientists are now discussing these possibilities in a very different tone compared to the past. Previously, the Fermi paradox was an academic puzzle, an intellectual game, a question asked at a lunch table, debated over tea, but never transformed into a genuine concern. Not anymore. In the last decade, some of the world's most prestigious scientists have begun approaching this question with a framework of existential urgency. Stephen Hawking said repeatedly, "If aliens find us, it might be something like Columbus landing in America." And that did not end well for the indigenous peoples. Names like Elon Musk, Nick Bostrom, and Max Tegmark have shared their concerns about the Great Filter and existential risk with the public. The Existential Risk Institute was established at Oxford University. A similar organization formed at Cambridge University. These people are speaking not to create panic, but to foster awareness. And this awareness is spreading to an ever wider community in recent years. This is what scientists have finally come to admit. Not just the universe is silent. Not just there are no aliens. Something far deeper. This silence is telling us something. And the content of that something is not hopeful but cautionary. But now let us come to the real question of this section. After hearing this warning, what do we do? Because this video is not merely a presentation of information. First, think about this. In all of human history, how many generations were able to ask these questions? How many generations looked at the sky and wondered what lay beyond it, yet could never come close to a real answer? Dozens of generations, hundreds of generations. Each one looked, each one wondered, but they did not have the tools. They did not have telescopes. They did not have the mathematics. They did not have the cosmology. We are the first generation, truly the first generation that can formulate the Fermi paradox, understand the Great Filter, detect exoplanets, listen to space, and genuinely analyze this silence. This privilege is not insignificant. It is an unprecedented position in the history of humanity. And with this position comes a responsibility. The real lesson of the Great Filter is this: intelligent life may not be rare. Starting may not be difficult. But continuing is very difficult. And the greatest obstacle to continuing is not a threat from the outside. It is a failure from the inside. Now look at the current state of humanity and be honest with yourself. Humanity is right now in the most critical region of the Great Filter. Nuclear weapons exist. Biotechnology is rapidly democratizing. Artificial intelligence is gaining momentum beyond expectations. Climate change is occurring, and none of these threats is being addressed separately. All of them exist simultaneously in an ecosystem where each affects the others. But at the same time, we also see this. There are people who are aware of these threats, who are studying them, seeking solutions, raising the alarm. And these people are no longer marginal. They are inside central institutions, the most prestigious universities, the most serious research communities. Existential risk research is now part of the academic mainstream. This change is important because awareness is the prerequisite for action. But awareness is not enough. We know this too. Here is where the most insidious aspect of the Great Filter appears. Having awareness is not sufficient to take action, because there is a vast gap between individual awareness and collective action. And this gap is the place where humanity has stumbled time and again throughout history. As the Roman Empire was collapsing, there are texts written by intellectuals who were watching it unfold. They saw it too. They understood it too. But the collective decision-making mechanisms did not function. Individual understanding could not overcome collective inaction. This pattern repeats, repeatedly, in different civilizations, in different eras. at different scales. Individuals understand. Groups understand. But the system does not transform, because systems transform not through individual awareness, but through structural change. And this is the collective action dimension of the Great Filter. If the Great Filter is real and lies ahead of us, overcoming it requires humanity to act not individually, but collectively. And in the history of humanity, there are very few examples of collective action at this scale. World War II, perhaps. Faced with one of the greatest threats humanity had ever encountered, different countries, different cultures, different interest groups came together. It was not perfect, but it worked. The threat was concrete. The threat was close. The threat was visible. The threats of the Great Filter, however, are usually abstract, distant, invisible, and this invisibility makes collective action harder. Think about climate change. There have been warnings for 50 years. There has been scientific consensus for 30 years. But sufficient collective action still has not come, because the threat is advancing slowly, because the costs are distributed, because the benefit is not in the short term, but in the long term. The same can be said for artificial intelligence. Experts are warning. Researchers are raising the alarm. But economic incentives, short-term competitive concerns, national interests, all of these push long-term safety to the background. This is humanity's deepest vulnerability. And perhaps this is also the deepest reason for the universe's silence. Every civilization must confront this vulnerability, and most fail in this confrontation. But now, in the middle of this dark picture, I want to touch on a very important truth. This video is not meant to drive you to despair. On the contrary, this video is meant for exactly the opposite. Because a civilization that is aware of the Great Filter is in a very different position from one that is not. A civilization that is unaware walks blindly toward that filter. It does not see it, cannot feel it, and one day it collides with it. But a civilization that is aware pauses, thinks, weighs its options, and perhaps changes direction. This awareness may be extraordinarily rare in the history of the universe. Perhaps most civilizations perished before ever reaching this point. Perhaps some reached it, but it was too late to change. And perhaps a vanishingly small number gained this awareness in time and used it. We are in that critical window right now, and we do not know how long this window will remain open. Now let us come to a very personal question. When you think about what you have learned in this video, this silence, this filter, what do you feel? Perhaps fear. Normal. It is frightening to think that throughout the history of the universe, countless civilizations have in all likelihood perished, that this perishing happened silently, that no trace was left, that none of them could warn the others. Perhaps helplessness. Understandable. As an individual human being, it is natural to feel that changing processes on a galactic scale is not possible. But perhaps you feel something else too. Perhaps, in the middle of all this darkness, something very small but very real. Meaning, connection, responsibility. Because think about this. Right now, at this very moment, billions of people are living on Earth. And the vast majority of them are never asking these questions. Never thinking about this silence. Never knowing about this filter. Simply living. Simply inside their daily lives. And you are watching this video. You are asking these questions. You have this awareness. This may seem like a small thing, but it is not. Because look at the way ideas spread. An idea is accepted by one mind. That mind shares it with another mind. That mind with another. And slowly that idea becomes part of the culture. It influences decisions. It shapes institutions. It changes history. This is the power of ideas. And the idea of the Great Filter is living through exactly this process right now. 10 years ago, existential risk research barely existed. Today, there are research centers at Oxford, Cambridge, and MIT. 10 years ago, AI safety was a marginal field. Today, it is on the agenda of the world's largest technology companies. 10 years ago, the Fermi paradox was only of interest to hobbyist astronomers. Today, scientists, philosophers, and policymakers are discussing this topic. This change came from nothing, from a few people taking these questions seriously. And this seriousness spread. You are part of this spreading too.